Okay, these are the notes for lesson 5-2. What we're going to see is a bunch of little theorems here. First thing we're going to talk about, the book is going to use the word distance between a point and a line. And if you look at any point, like point A here, and a line, they're going to assume you know what the distance is. And realistically, you can go, well, is it this distance? Is it this distance? Is it this distance? Well, when they use the word distance between a point and a line, they are going to be talking about the perpendicular distance. So I know it's kind of vague, but they are talking about the shortest distance perpendicular to it. Okay? So now be aware of that when you get to problems on the work. Theorem 5-2, perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, so I got a point X here, and if I'm on the perpendicular bisector of a segment, then it is equidistant to the endpoints. So then this point X is the same distance here to here as here to here. So I would have a tick and a tick here. If I'm sitting on anywhere on this perpendicular bisector, then if I connect to the endpoints of that segment, they would be equal. And we're going to put that in reverse, the converse of the perpendicular bisector theorem. If you notice, there's a point A up here, and I notice, you know what? I got a tick mark here and a tick mark here. I'm equidistant to the endpoint of this segment. Then this point A must be lying on the perpendicular bisector. So then this has to be 90 degrees, and it has to be a tick mark there and a tick mark there. Okay, that is the perpendicular bisector theorem. There's going to be another theorem here based on the angle bisector. If a point is on the bisector of an angle, so I'm just sitting here and I'm point X, but you notice that's 30 degrees, this is 30 degrees, this must be the angle bisector. If this is the angle bisector, then it is equidistant to each side of the angle. So point X here would be the same distance to the sides, the top side here and the bottom side of the angle. So I'm going to draw a line. Now when we use the word distance, we're talking about this 90 degree shortest distance. That guy there and this guy here are going to be the same. So I'll put a tick here and a tick here. They are equidistant to the sides of the angle. We're going to put that theorem right there in reverse, the converse of the angle bisector theorem. So I got a point here. I notice this distance, 90 degrees tick, is equal to this distance. So maybe it's 2 inches here, 2 inches here. If a point is equidistant to each side, then this point, I didn't put a letter there, but this point X is on the angle bisector. So then this line must have been tick mark, the angle bisector. Okay. Alrighty, let's go answer one last problem here. According to the diagram, how far is K from EH? Where's K? K is right here. Here's EH. According to this diagram, it's 10. I don't know what's so hard about that. And how far is it from E to D? Well, there's double tick mark here, there's double tick mark here. This must be 10 as well. What can you conclude about EK? Well, because I am equidistant to this big, here, let me use a color here. This color is going to come in. Because I'm equidistant to this pink angle, I'm 10 inches here, I'm 10 inches there. This line, EK, must be the angle bisector. This point K must be sitting on the angle bisector. It splits this pink angle perfectly in half. Then it says find the value of X. Where's X? So we just said it's angle bisector, so this top portion is equal to the bottom portion. So I can say 2X is equal to the bottom portion. X plus 20. Looks like X is going to equal 20 there. Then they want us to figure out the angle of DEH. Well, if I put a 20 here, this top part is 40 degrees. And then if I put a 20 where X is, again, 20 plus 20 is 40. So together, DEH is 40 plus 40, 80 degrees.